construction process. Back at the staging area for Shaft L, site conditions required excavating through 80 feet of soil, using the slurry wall method for temporary support. The slurry wall was constructed by digging sections of trench around the shaft and filling them with a liquid bentonite mixture called slurry. The slurry prevented the banks of soil from caving in as each trench was excavated down to rock level. As the excavation of each trench section was completed, a steel-reinforced cage was placed in the trenches and the concrete was tremmed into the bottom of the panel, displacing the slurry as it was added. The multi-sided wall is made up of individual panels, each requiring a separate concrete placement. When all of the panels were set, they formed a reinforced concrete ring around the shaft site. Then soil was removed safely from inside the wall. From the top of the rock, the rest of Shaft L was excavated another 330 feet using the drill and blast method. To drill and blast, miners drilled holes about 2 inches in diameter and 8 to 10 feet long down into the rock of the shaft floor. Then they filled the holes with explosives, evacuated the shaft, and detonated the blast. The resulting rock rubble, called muck, was removed in buckets, hoisted by crane to the top of the shaft. Rock bolts and wire mesh were installed as needed to prevent rock from crumbling from the sides of the shaft. Then shotcrete, a pneumatically applied concrete, was applied to the surface to strengthen the rock support. At tunnel level, the miners drilled and blasted the east and west walls of the shaft to construct a starter chamber for the tunnel boring machines. Here, all of the backup equipment and the systems necessary to support each of the mining operations were installed. A ventilation line to bring air to the tunnel, pumps to remove inflowing water, electric systems, an air scrubber to settle rock dust and purify the air, a railway system to transport materials, equipment, and workers, and a conveyor for rock removal. Shaft L, the passageway for all workers and materials entering and exiting the middle section of the tunnel, is a very busy place. Here, the tunnel boring machines, called TBMs, were carefully lowered down the shaft in sections. In the launch chamber, tunnel workers assembled the TBM components and prepared them for startup. The body of a TBM resembles a flat-nosed rocket ship. The cutter head is equipped with steel cutter wheels that carve out the hard bedrock as the head is rotated. The trailing gear contains the mechanical components and the hydraulic and electric systems that operate the head. Grippers stabilize the TBM against the tunnel wall. The operator's console area houses the control systems. During mining, the operator uses state-of-the-art laser technology to maintain the correct alignment. The beam targets the rock face, centering the cutter head on the correct line and grade. One shove of the TBM, called a stroke, pushes the cutter head about 5.5 feet into the bedrock. As the cutter head rotates against the face of the tunnel, it carves out about 45 cubic yards of rock per stroke. Rock rubble from the head drops onto the TBM muck conveyor. The TBM conveyor is connected to a series of horizontal and vertical conveyors that transport the rock to the surface of the shaft for removal. As each stroke is completed, the operator relaxes the grippers and advances and resets the TBM for the next shove. According to the results of an extensive geotechnical study, the TBMs are tunneling through some of the hardest, most abrasive rock in the United States and across 2 major fault lines. Workers evaluate the need for rock support as the mining operation continues. Rock bolts, wire mesh, steel ribs, and shotcrete are available to stabilize any fractured or crumbling rock. And in areas where water inflows exceed a specified number of gallons a minute, they'll perform a grouting operation to cut off the water flows. First, the miners drill holes into the sides of the tunnel. Then they place packers in the holes and inject grout to physically seal cracks in the rock. The design plan of the Metro West Tunnel includes the construction of 5 riser connections linking the new tunnel to local community water systems. As the tunnel operation reaches these locations, 3 in Framingham, 1 in Southborough, and 1 in Weston, the risers will be excavated, and some will serve as emergency exits during construction. When the 17.6-mile excavation is completed, the tunnel boring machines will be disassembled and hoisted in sections through the shafts to the surface. The tunnel will then be lined with 1-foot-thick cast-in-place concrete. First, concrete forms are assembled in sections which can be collapsed, moved ahead, and reset as the lining operation progresses. Batch plants constructed at 2 shaft staging areas will supply the concrete for the tunnel lining. The concrete will travel underground through a system of pipes and conveyors to the concrete placing bridge. Here, a concrete pump feeds the concrete into a pipe called a slick line, which is connected to the top of the forms. As the concrete is pumped, it moves through the slick line, filling in the forms. The entire concrete placing bridge moves backwards as concrete is placed and the forms filled. As the concrete is placed in each section of the tunnel, work crews will line the shafts and risers. Steel lining will be installed inside the slurry walls at the upper part of the large diameter shafts. Reinforced cast-in-place concrete will support the rock walls of the lower sections. The small diameter riser shafts will be lined completely with steel. Once the lining is in place and the tunnel is finished, it will be filled, pressure tested, and disinfected. Then, Quabbin water, released to the system, will follow a new path as it travels 17.5 miles through the Metro West Tunnel on its journey to consumers in the MWRA service area. Throughout the construction process, the health and safety of our workforce is a crucial concern. Tunnel construction exposes workers to unique hazards in a congested and confined underground enclosure. To reduce the risks of personal injury, we've developed a comprehensive program that integrates safety principles into all aspects of project work. Required safety equipment, employee safety training, and emergency response plans coordinated with local fire department and rescue teams all reflect our efforts to create a safe working environment. Today, the construction of a supply line first conceived more than half a century ago is underway. The Metro West Tunnel will provide critical backup transmission to protect us all from a water supply disaster. Once the new tunnel is in place, the Hultman Aqueduct can be removed from service for inspection and repair. The new tunnel is the keystone of our integrated waterworks improvement program. It prepares the connecting links for all the other major projects designed to improve our water quality and assures that our water supply system supports our economic vitality and protects our quality of life.
Good water supply is the key to quality of life in every one of our homes. And it's the key to a sound economy for every business and industry in our area. We have many things to do to make our water supply strong, but the tunnel is the most important. So now we're well on our way to having the water system that we should have for the metropolitan area in the 21st century.
As we carry out our mission to modernize the region's water system, we're preserving the gift of a previous generation, the Quabbin Reservoir. And we're enhancing it with a long-lasting legacy of our own. A pure, reliable, and bountiful water supply for generations to come.